Hello friends, welcome to lecture number 11 of Electricity and Magnetism LCR circuit. So this is our topic and resonance frequency. We're going to discuss about resonance frequency. So now before we start, please subscribe the channel, hit the thumbs up button if you like my videos, and share with your friends. Help me to grow my channel, inspire me to create new contents for you. And if you are new to my channel, please subscribe the channel and also hit the bell icon so that you get notified when new video will be uploaded, right? So now let's start. Suppose we have a circuit containing inductance. Suppose we have an inductor with inductance L, capacitor of capacitance C, and resistor of resistance R in series, okay, and connected with an alternating source, right? So alternating voltage source E is equal to E naught sine omega t, we have supposed like that, okay. So now you see, so I have written what I have considered here. So this is the inductance of the inductor, capacitance C of the capacitor, and we have also considered QB, the charge on the capacitor at an instant t, and at the same instant I is the current in the circuit. We have considered like that, right? So now you see induced EMF due to self-induction L, that will be minus L di by dt, right? Because it opposes the cause of induced EMF, that is it gonna be in opposite to this applied EMF, right? So, and in capacitance, we know capacitance C is equal to given by Q by V, and V will be Q by C, and which is again opposite to this applied EMF, so Q by C, right? And according to Ohm law, that voltage across this resistance, that will be Ri, right? R into I, okay. So here you see, so we're gonna write that back EMF due to self-inductance L is given by L di by dt, right? And here you see potential difference across the capacitor, potential difference across the capacitor, that is given by Q by C, and therefore here you see, since both being opposite to applied EMF, so effective EMF will be given by, E naught, which is the applied EMF, E naught sin omega t, minus L di by dt minus Q by C. If this is the applied EMF, E is equal to E naught sin omega t, and these two oppose it, therefore this Ri must be equal to this effective EMF, right? So therefore we can write, let me take a new slide, we can write this is equal to, let me copy this is equal to R into I, right? So here you see, we have applied E naught sin omega t, right? And induced EMF here due to the self-induction is L di dt, and here across the capacitance C, it is Q by C. So therefore the resistance, potential difference across the resistance, that Ri must be equal to it must be equal to this applied EMF minus this induced EMF and the potential difference across the C, right? So hope you have understood this. So now you see, so let me rearrange this equation in this form. Let me transfer these two terms on the other side. Then what you will get? Then you will get L di by dt plus Ri plus Q by C is equal to E naught sine omega t. E naught sine omega t, right? So here you see, differentiating, if you differentiate it again with respect to t, we get L second order derivative of I with respect to t, then plus R di by dt, then R di by dt plus 1 by C dq by dt is equal to, if you differentiate this, then what you will get? E naught omega cos omega t, right? You're gonna get this, okay? So from here, that we can replace this dq by dt by I, because I is equal to dq by dt, rate of flow of charge, right? So we can write L second order derivative of I with respect to time t, then plus R di by dt plus 1 by C. So it can be replaced by I. dq by dt is replaced by I, E naught omega cos omega t. So what we have done, we have written, since this dq by dt is equal to I, that's why we have replaced this dq by dt by I. So hope you have understood this. Now this is suppose equation number 1, right? So in the steady state, the current alternates with the same frequency as the applied EMF, but may be differ in amplitude, right? So if this is the applied EMF, right, the current across this current in this circuit will alternate with the same frequency as this applied EMF, but amplitude and phase may be different, right? So if this is your suppose EMF, then this can be your current. Different phase and maybe amplitude may be different, okay? So hope you have understood. So now you see, now the solution of this kind of differential equation we can consider as, so let the solution of equation number 1 be of the form I is equal to I naught sine omega minus phi. Phi is the phase differ from the phase of the applied EMF, right? So phase of current and applied EMF be suppose differ by this phi, okay? So let us consider that way. Then let me go to the next slide. So here where I naught and phi are constants to be determined. So here we are to determine these two. Are to be determined. So now if we differentiate this equation, so here you see, so this is suppose equation number 2. If you differentiate this equation number 2, let me write on the other side. So here we go. So this is the equation number 2, right? So if you differentiate equation number 2 with respect to t, then what you're gonna get, di by dt is equal to I naught omega cos omega t minus phi, right? So differentiating this, we have got this result. So now if you differentiate it again, then what are you gonna get? You're gonna get minus I naught omega square, instead of cos now it becomes sine omega t minus phi. That's what we will get, right? So now substitute, if you substitute this to value di by dt and second order derivative of I with respect to t in equation number 1, if you use this to value here, let me go to previous slide. So if you use this to value here, then what you will get, right? Using this in 1, that means let me take this equation number 3, right? So let me take this as equation number 3. Using 3 in 1, what we're gonna get, then we are to get, so this is what we have got, right? So what we have done here, you see, let me write this equation number 1 on the next side. This is the equation number 1, right? Let me copy this thing. Okay. So here you see, let me write here, this is the equation number 1. So what we have done, we have replaced this by this value, right? And we have replaced this by this value, and also we have replaced this I by this value of I from 2. So what we have to write here, so not only 3, we have used 2 and 3 both, right? Using 2 and 3 in 1, right? So that's how we have got this equation, putting these two in equation number 1. So we don't need this here, so just let me delete this. You can take I naught sine omega minus phi common, right? I naught sine omega t minus phi, let's take common from these two terms. So then what you will get, and so on the right hand side you see, we can write this omega t as omega t minus phi plus phi, right? We can express that way also. Now here you can you see, we have written this omega t as omega t minus phi plus phi, that's going to be again omega t, right? So now considering this as cos a plus b, so applying the identity of cos a plus b, then what you will get, so you're going to get, so this is your right hand side, this is what you will get. So what we have done here, we have applied this cos of a plus b identity, that is cos a cos b minus sin a sin b, right? We have used this identity here. Okay, so now, so let me write the final equation on the other side, on another slide. Okay, this is the result we have got after simplification, and this equation is true for all t, so that's why we can write this. So now you see, equating the coefficients of sine So if you compare the coefficients of sine omega t minus phi, this is sine omega t minus phi on the either side also. Here you see sine omega t minus phi. So in this side, here you see on this side its coefficient is this, and on the right hand side its coefficient is minus e naught omega sine phi, right? So that's why comparing its coefficients of sine omega t minus phi. So what we're gonna get? We're gonna get minus L omega square plus 1 by c I naught is equal to minus e naught omega sine phi, right? And similarly comparing the coefficients of this, so we're gonna get r omega I naught e naught omega cos phi. So if you take the right hand side coefficient of this on the right hand side, so you can see its coefficient will be e naught omega cos phi, right? And on the left hand side here you can see this is the cos omega t minus phi, its coefficient is this. So this must be equal to e naught omega cos phi, right? So hope you have understood this. So now let me take this as equation number 4 and this is equation number 5, right? Now let us divide equation number 4 by equation number 5, and doing so what you will get, you're gonna get, you see that sine phi by cos phi, that will be 10 and these two will be cancelled, right? If you divide these two equations, okay, so then minus will be on the other side, you can write. So this minus can be written on this side, right? So what you will get, then this minus is gonna be plus and this is gonna be minus, right? So we will get 10 phi, that is sine phi by cos phi, right, is equal to minus, here minus L omega square plus 1 by c by r omega, and this I naught gone, right? So hope you have understood this. So we have got these things. So now you see, so you can just simplify this as, let me copy this and let me go to the next slide. Okay, let me copy this result. Okay, and then let's go to the next slide. So here is the result we have got, and it can be simplified as, you see, this minus it's become plus and this will be minus, right? So let me write it that way, just wait. So let me multiply the minus sign, right? That's what we will get. Then let us take omega common from the numerator, from the both term of the numerator. Then what you will get, 1 by omega c omega, right, by r omega, and this omega gone. So what we have got, L omega minus 1 by omega c by r, right? Let it be equation number 6, and squaring and adding equation number 4 and 5. So equation number 4 and equation number 5 is squaring and adding. Okay, this is the equation. Just let me write this way. So equation number 4 is squaring this equation and adding with the square of the equation of number 5, squaring and adding. What you will get, you're gonna get, here you see, so if you square this equation, what you will get, square here, and here, right? And similarly here also, if you square this, you're gonna get this result. Then if you add these two equations, you can take e naught square omega square, e naught square omega square common on the right hand side, right? And then you will get, then what you will get on the right hand side, what you will get, on taking e naught square omega square common, you will get sine square phi and cos square phi, right? Sine square phi plus cos square phi, that's what you will get. And on the left hand side, squaring on the left hand side, if you square this whole thing, then this minus will be plus, right? Then squaring this, what you will get? R square omega square I naught square. So our left hand side will be it can be written as this I naught is taken common, you can consider that way. So here also I naught, here also I naught square will be taken common. So I naught square minus here you can see minus L omega square plus 1 by C whole square, right? Whole square, then plus R square omega square. That's what we will get on right hand side, left hand side. So here you see sine square plus cos square, sine square phi plus cos square phi, that's going to be 1. So if you want to remove this term, then you can remove, right? So now you see, if you simplify this, then here again you see, if you divide both sides by omega square, if you divide both sides by omega square, right? So there will be omega square, there will be omega, omega is this, you can write that way, omega square. So then what you will get, when you will write this inside this whole bracket, then you will get, here you have to write omega, right? So then here also omega square, right? Dividing both sides by omega square. So that's what we will get, right? So we're gonna get, just wait, or you can consider that way also, L omega minus plus 1 by omega C. You can take common omega. So here we have square, that's why when you take omega common from these things, these two terms inside the bracket, then here you have to write, outside the bracket you have to write omega square, right? So as there is a square here, right? So hope you have understood this. So now plus R square omega square E naught square plus omega square. So dividing both sides by omega square. So here you see, this is not plus omega square into omega square. So dividing both sides by omega square. So our final equation will be I naught square minus L omega plus 1 by omega C whole square plus R square is equal to E naught square. And from here you can write I naught is equal to, that is current, I naught is equal to, so E naught by root over R square plus minus L omega plus 1 by omega C plus 1 by omega C whole square. Let it be suppose equation number 7. Now use this equation here. Here you can use this equation. Let me write it. In equation number 2, you can put the value of I naught, that what you have got here. You can see this is the value of I naught, right? You can use that way using 7 in 2. So let me go to another slide. So using equation number 7 in 2, we have got, so let us take this as equation number 8, and here phi will be equal to, so we can obtain the phi from here, you see, from this equation number 6. From equation number 6 you can find phi. Phi will be equal to tan inverse of this, right? So from equation number 6 we can write from equation number 6 what do we get? Phi is equal to tan inverse omega L minus 1 by omega C divided by R. That is what we will get. And the I naught, the value of I naught, this you can see, this gonna give you the amplitude of current. or maximum current. Right, so that's what you will get in this equation. Now you see this quantity that you have got in the denominator, this is called impedance, right? This quantity is called impedance. So let me write here. So this is equation number 8. So root over r square plus omega L minus 1 by omega C whole square is called impedance, that is represented by Z, called impedance, right? And this quantity here you see, this quantity is the resultant resistance of the circuit, which is the difference between the inductive reactance. And so here actually you see this XL represents inductive reactance. We have already discussed in the previous lectures. Okay, link of those lectures are given in the description box. If you want to what's done, you may go through them. So this is XL and this term is XC, right? So we can write on the other side that impedance Z is equal to root over R square plus XL minus XC whole square, where XL is equal to omega L, which is inductive reactance, and XC is 1 by omega C, which is capacitive reactance. Right, so we have understood this. So similarly, this phi, you see this phi, value of phi, here also you can replace this this one by in terms of you can write this in terms of XL and XC, right? So what you can write phi is equal to XL minus XC divided by R. That's what you can write. So hope you have understood this. So sorry, tan inverse, I forgot to write this tan inverse. Okay, so this is the phase, right? This is the phase angle, right? So now you see, let me take a few cases here. So case 1, if or when case 1, when XL is greater than XC, then current lags behind the applied EMF. So phi will be positive, phi is positive, and current lags behind E, right? So here you see, if you get phi positive, if you put here, so you can see clearly E is equal to E naught sine omega t, right? And we are getting here minus phi, sine omega t minus phi. If phi is negative, then this minus it will be plus, right? Then current will lead, right? So when case 2, when XL less than XC, then phi is negative, the current, you can see clearly from here, if XL is less than XC, if this one is less, XL is less than XC, then this phi will be negative, and if this phi is negative, if you put here negative phi here, then this sine omega t minus, instead of phi, if you put minus phi, then it will be plus phi. Then this current will lead the EMF by phi, right? So hope you have understood this. Now case 3. Now let us discuss about case 3. So case 3, let me write here case 3. So in this case, case 3, if XL is equal to XC, then you see the phi will be 0. Then phi will be 0. Then current and the EMF will be on the same phase. Then current I and EMF are in same phase. So hope you have understood this. So you can see, okay, let me go to the next slide. This condition where XL is equal to XC, this is called resonance condition. Okay, this is condition of resonance. Condition of resonance. Because here you see the phase of I and E both are in the same phase. Okay, so XL means that omega L, and XC is omega C, 1 by omega C, and from here you will get omega square is equal to 1 by L into C, and omega will be equal to 1 by LC, under root LC, right? 1 by LC. So, or you can write 1 by root over LC. So again, that frequency F, we know that omega is equal to 2 pi F, right? So if you put that omega is equal to 2 pi F, here 1 by root over LC. Okay, since what we have got, since we have used here omega is equal to 2 pi F, right? So from here your F will be equal to 1 by 2 pi root over LC. That's what we will get. And so this whole thing you're going to consider as F naught, which will represent the natural frequency. This is natural frequency. So hope you have understood. This is all about series LCR circuit. So thank you for watching. Stay connected. If you like my videos, please share with your friends if you think these videos are helpful. And if you are new to my channel, please subscribe the channel, hit the bell icon so that you get notified when new video will be uploaded. And please help me to grow my channel. So thank you for watching. Take care.